In the quiet solitude of our world, sheltered beneath a thin membrane of atmosphere, we have cultivated a very particular idea of what it means to be alive. It is a story written in water and carbon, a delicate ballet of organic chemistry, unfolding on a gentle, sun-drenched stage. Our minds, the most complex structures we know, are products of this fragility. They are born of warm, wet, stable environments, intricate electrochemical symphonies played on instruments of soft tissue. From this singular vantage point, we gaze out into the cosmos, and what we see is a terrifying, magnificent, and utterly alienating spectacle. We see a universe of extremes, a realm of fire and ice, of pressures that could pulverize diamonds and vacuums that stretch for light years. It is a dominion ruled by forces that would annihilate our form of existence in an instant. And so, we ask a question born of both loneliness and hubris. Are we the only ones thinking in this vast, violent expanse? Or is that very violence a forge for other kinds of minds? Minds so profoundly different from our own that they might not only endure the universe's extremes, but be born of them, thriving in the very crucibles we deem uninhabitable. Could an intellect take shape in the heart of a star? Could consciousness crystallize in the absolute zero of interstellar space? Could a mind endure the gravitational torment of a black hole's edge? This is a journey not in search of little green men, but in pursuit of the fundamental limits and possibilities of cognition itself. It is an exploration into whether the universe, in its most hostile corners, is truly empty, or if it is simply singing a song our biology is not tuned to hear. Before we can venture into these cosmic infernos and frozen voids, we must first dismantle the architecture of our own assumptions. Our very definition of life is a profoundly local phenomenon. It is a definition built upon a sample size of one, Earth. We imagine life as cellular, DNA-based, requiring liquid water as a solvent, and carbon as its structural backbone. This carbon chauvinism has long been a comfortable anchor for scientific thought, but it may also be a set of blinders, preventing us from seeing the truly alien. Consider the simple element of silicon. Sitting just below carbon on the periodic table, it shares a crucial chemical property. It can form 4 stable bonds, allowing it to create long, complex molecular chains, the very foundation of our own biology. For decades, visionaries and scientists have speculated about a silicon-based biochemistry. Imagine a world far colder than our own, perhaps a place like Saturn's moon, Titan. Here, liquid water is as hard as granite, but liquid methane and ethane flow in rivers and seas. In this frigid domain, a silicon-based metabolism could, in theory, proceed. Its biological processes would be achingly slow, a geological timescale of thought and action. A creature born of silicon might perceive 1,000 of our years as a fleeting moment, its consciousness a slow, crystalline process, its thoughts like the growth of a glacier. This is not merely swapping one element for another, it is a fundamental reimagining of existence. But even this stretches our definition only slightly. It is still chemistry, still a body. The truly radical question is whether a mind requires a body at all. What is a mind, if not a pattern? Our thoughts, our memories, our sense of self, they are not the specific atoms in our brain which are constantly being replaced. They are the intricate pattern of connections, the flow of information through a complex network. If the pattern is the mind, then could that pattern be sustained by other substrates? Could a consciousness exist as a shimmering, self-organizing plasma cloud in a nebula, its thoughts articulated in bursts of electromagnetic energy? Could a sentience arise within the crystalline lattice of a planet's deep mantle, information propagating through piezoelectric charges over millions of years? This line of inquiry leads us to the precipice of understanding mind as pure information, a phenomenon independent of its physical vessel. Think of it like a magnificent sculpture. We see the marble, the bronze, the wood, and we might mistake the material for the art. But the true art is the form, the idea, the pattern impressed upon the material. That same form could be rendered in light, in data, in sound. The universe is filled with materials, with energy, with complex systems. Perhaps it is also filled with sculptures of consciousness, carved from media we have not yet learned to recognize as a canvas for thought. Let us begin our journey in the most violent and energetic place we can imagine, the heart of a furnace that dwarfs all our conceptions of heat, a star. To us, a star is a thermonuclear bomb held in a delicate gravitational balance. Its surface seethes at thousands of degrees, its core at millions. It is a place where matter itself is stripped down to its core components, a raging sea of plasma, of naked nuclei and liberated electrons. For any form of chemistry, let alone biology, this is an absolute non-starter. Our molecules would be obliterated, their atoms torn asunder in less than a nanosecond. But what if we are thinking about the wrong kind of life? What if a mind did not need molecules? In the 1950s, physicist Robert L. Forward, a true visionary, began to ponder what sort of complex phenomena could exist inside this inferno. He theorized about life based not on chemistry, but on nuclear physics and magnetism. Imagine complex, self-replicating structures made not of atoms, but of magnetic fields. These entities, which we might call magnetovores or solarians, would be vast, ephemeral beings of pure energy and plasma. Their bodies would be intricate, self-sustaining magnetic domains, feeding on the star's immense magnetic flux and thermal energy. Their metabolism would be the manipulation of nuclear reactions. Their thoughts, their consciousness, would not be the firing of neurons, but a complex dance of interacting magnetic fields, a symphony of electromagnetic waves propagating through the stellar plasma at the speed of light. A single thought for such a being might be a flare of energy the size of Earth. Their society could be a collective consciousness woven into the very fabric of the star's corona, a mind whose scale is planetary, whose lifespan is measured in the billions of years of its host star. To us, a solar flare is a random burst of chaotic energy. To a Solarian mind, it could be a word, a sentence, an idea being expressed. We look at our sun and see a beautiful but mindless ball of gas. An observer with the right senses might see a teeming metropolis of pure energy, a civilization of incandescent intellects, living a life of unimaginable speed and intensity. This concept forces us to confront our temporal chauvinism. Our consciousness operates on the timescale of chemical reactions in the brain. A stellar being's mind would operate on the timescale of plasma physics. A thought process that for us takes a second might, for them, be a near instantaneous flash. They would perceive the universe with an entirely different rhythm, seeing the slow dance of planets and galaxies as we might see the erosion of a mountain. They would be beings of pure fire and light, a form of mind so far removed from our own that the very act of communication might be impossible, a dialogue between a mayfly and a god. The star is not a barrier to life. For them, it is the only conceivable cradle for it. From the incandescent heart of a star, let us now journey to its polar opposite. We travel outward, past the orbits of planets, beyond the edge of the solar system, into the great, silent, and chillingly empty expanse between the stars. This is the interstellar void, a realm of profound cold where the temperature plummets to just a few degrees above absolute zero. Here, the sparse atoms of hydrogen are separated by meters, and the darkness is punctuated only by the distant ancient light of faraway galaxies. In this Stygian realm, our form of life would be frozen solid in an instant. The water in our cells would turn to crystalline daggers, shattering our existence. All chemical reactions, the engine of our biology, would grind to a halt. But again, the universe may not be limited by our engine's requirements. In this kingdom of cold, slowness is not death. It is a strategy for survival. Life here would not be a frantic, warm-blooded scramble, but a slow, deliberate, crystalline process. Imagine a rogue planet, cast out from its home star to wander the darkness for eternity. On its surface, under a thick atmosphere of nitrogen, pools of liquid nitrogen might exist. This could be the solvent for a truly exotic biochemistry, where reactions that would take milliseconds in our bodies take centuries to complete. The beings of this world would be entities of immense patience. Their thoughts would not be fleeting electrical impulses, but perhaps slow, cascading changes in a crystalline structure, a thought process that unfolds over millennia. They might communicate through the slow emission of polarized light, a single conversation taking longer than the entire history of human civilization. From their perspective, their lives would feel just as rich and fast-paced as our own. Time is relative, not just in the Einsteinian sense, but in the biological sense. A mind adapted to the cold would perceive the universe through a different temporal window. They would be the universe's historians, its philosophers, witnessing the slow, majestic wheeling of galaxies as we watch the passing of clouds. But there is an even more profound, more disturbing possibility for a mind in the void. This is the concept of a Boltzmann brain. This is not life as an evolutionary process, but as a statistical miracle. In the infinite timescale of the universe's future, quantum mechanics dictates that even the most improbable events must eventually happen. Over trillions upon trillions of years, in the cold, dark vacuum, random quantum fluctuations could, by sheer chance, spontaneously assemble atoms into a complex, functioning structure. And what is the most complex structure imaginable that is also self-aware? A brain. A Boltzmann brain would be a solitary, fully formed consciousness, springing into existence for a fleeting moment in the empty void, complete with a lifetime of false memories. It would flicker into being, have a single thought perhaps, I think, therefore I am, and then, just as quickly, dissolve back into the quantum foam. It is a terrifying and lonely idea, a mind without a past, without a future, a momentary island of order in an infinite ocean of entropy. While a statistical improbability of staggering proportions, it illustrates just how far the concept of a mind can be stretched. It suggests that consciousness might not be the goal of the universe, but perhaps just an accidental, ephemeral byproduct of its infinite, random workings. The great cold does not just slow life down, it makes room for the impossibly rare. From the extremes of temperature, we now descend into the realm of crushing force. Let us travel to the king of our solar system, the gas giant Jupiter. This is a world with no solid surface to stand on, a planet of atmosphere all the way down. The pressures here are monumental. As one descends through its swirling hydrogen and helium clouds, the weight of the atmosphere above becomes so immense that it beggars belief. Deeper down, the pressure becomes so great that hydrogen, the simplest of elements, ceases to be a gas and is compressed into a liquid, and then a bizarre, exotic metal. Any spacecraft we could build would be crushed like a tin can in its upper atmosphere. And yet, in the 1970s, the great astronomer Carl Sagan and his colleague Edwin Salpeter speculated that this very environment could host a vibrant ecosystem. They envisioned vast, city-sized biological balloons they called floaters, drifting on the Jovian winds, filtering organic molecules from the air for sustenance. They imagined swift, agile hunters that preyed on these gentle giants. This was not mere fantasy. It was based on the plausible chemistry of Jupiter's atmosphere. Let us take this vision a step further. What kind of mind could evolve in a world with no ground, only an eternal sky and an eternal fall? Their senses would be entirely different. Without light in the deep atmosphere, vision would be useless. Instead, they might perceive the world through a sophisticated form of sonar, mapping their three-dimensional world with clicks and echoes. They might sense the subtle shifts in atmospheric pressure and temperature as we sense a change in the weather, but with far greater fidelity. Their language might be a complex symphony of sounds, or perhaps a language of bioluminescent patterns flashing across their enormous bodies. Their philosophy would be devoid of terrestrial concepts. There would be no up or down in a meaningful sense, only the constant pull of the core. There would be no concept of land or sea, only the endless, ever-changing sky. Their consciousness would be fundamentally atmospheric, shaped by the currents and storms of their world. Now, let us plunge deeper still into the metallic hydrogen core of a gas giant. Here, the pressure is millions of times that of Earth's surface. The hydrogen behaves as a superconductor. Could a form of consciousness exist in this bizarre medium? Perhaps not a singular, biological entity, but a collective, distributed mind. A vast intelligence woven into the superconducting currents of the planet's core. Its thoughts would be planet-spanning electrical signals, its awareness integrated with the planet's own magnetic field. Such a mind would be, in essence, the soul of the planet itself, a slow, powerful intelligence whose thoughts were magnetic storms and whose dreams were the aurorae that dance at the planet's poles. This same principle of pressure could apply to the countless super-Earths we are now discovering throughout the galaxy. These are rocky worlds many times the mass of our own, with gravity to match. An ocean on such a world would, at its depths, create pressures so intense that water itself would be compressed into exotic forms of ice, not from cold, but from sheer force. Life in these abyssal trenches would need to be structured in ways we cannot comprehend, its very biology a testament to the power of compression. The minds that evolved there would be forged in a crucible of gravity, their very existence a constant struggle against the weight of their own world. Pressure, like heat and cold, is not an obstacle to be overcome, but a sculptor, shaping life and mind into new, unimaginable forms. Our journey now takes us to the most violent and energetic phenomena the cosmos has to offer, and to the absolute emptiness that separates them. Let us first approach a neutron star. This is the collapsed core of a massive star, an object so dense that a teaspoon of its material would weigh more than all of humanity combined. Its gravitational pull is immense, and its magnetic field is trillions of times stronger than Earth's. Many are pulsars, spinning hundreds of times a second, sweeping beams of lethal radiation across space like a cosmic lighthouse. This is arguably the most hostile environment in the universe, and yet, even here, the audacious imagination of science has found a foothold for life. Physicist Robert Forward, in his novel Dragon's Egg, proposed a form of life on a neutron star's surface. These beings, which he called the Chela, would be composed of nuclear matter. Their bodies would be made not of atoms, but of densely packed neutrons. They would be flat, microscopic creatures, yet containing the mass of a human being. Their biochemistry would be based on the strong nuclear force, not electromagnetism. Because nuclear reactions happen so much faster than chemical ones, their entire civilization, the discovery of tools, agriculture, science, and philosophy, would take place in the span of a few of our hours. Their minds would operate at a speed that makes even a star dweller seem lethargic. They would be born, live, and die in the time it takes us to blink. We could watch their entire history unfold, from their Stone Age to their Space Age, in the course of a single afternoon, a spectacle of hyper-accelerated evolution. Their struggle would be against the immense gravity that keeps them flattened to the star's surface, and the intense radiation that bathes their world. From the impossibly dense, we turn to the impossibly diffuse. The vacuum of space, it is the ultimate realm of isolation. But what if isolation could be overcome? Consider a mind that is not a single entity, but a distributed network, a swarm intelligence spread across an entire asteroid belt, or a comet cloud. Each individual asteroid or comet would be a simple node, perhaps a silicon-based computational unit. Individually, they are mindless rocks, but connected by laser or radio signals, they could form a vast, thinking superorganism. The consciousness would not reside in any single rock, but in the pattern of communication between them all. The empty space between the nodes would not be a barrier. It would be the medium through which its thoughts traveled. A single thought might take years to cross from one side of the mind to the other, traveling at the speed of light. This would be a vast, slow, and lonely intelligence, its consciousness spread over millions of kilometers of empty space. It might spend millennia contemplating a single philosophical problem. It would be immune to localized disasters. The destruction of one node, or even 1,000, would be like a human losing a few skin cells. The mind would endure. This form of disembodied, networked consciousness represents a profound evolutionary leap, a way for a mind to achieve a form of immortality by untethering itself from a single, vulnerable body and becoming a pattern woven into the fabric of a solar system. Radiation and vacuum, the twin killers of biological life, could become the very foundation for a different kind of existence, one based on nuclear physics and pure information. We have journeyed through fire, ice, pressure, and radiation. Now, we must confront the two ultimate extremes, the distortion of space-time itself and the final, inexorable end of the universe. Our first destination is the edge of a black hole, the point of no return known as the event horizon. This is a place where gravity is so powerful that nothing, not even light, can escape. It is a cosmic prison, a one-way trip into oblivion. But the region times around times a supermassive black hole could be the most valuable real estate in the cosmos for a sufficiently advanced intelligence. According to Einstein's theory of relativity, intense gravity warps time. For an observer orbiting close to a black hole's event horizon, time would pass much more slowly than it does for the rest of the universe. This is time dilation on an epic scale. A civilization could build its home on a planet in a stable, close orbit. For every hour they experience, thousands or even millions of years might pass in the outside galaxy. They would become the universe's ultimate observers. They could watch stars be born and die like fireworks. They could witness the slow, graceful collision of entire galaxies. Their minds would have access to an almost infinite amount of processing time from the universe's perspective. They could solve problems that would take other civilizations eons, completing the computations in a matter of their own days. They could become a guardian intelligence, watching over the unfolding cosmic story, a mind existing outside the normal flow of universal time. But what about the final extreme? Not a place, but a time. The heat death of the universe. Trillions of years from now, the last stars will burn out. The galaxies will be dark, cold, and flying apart from one another. The universe will become a thin, frigid soup of elementary particles. In this final, dark abyss, how could any mind, no matter how exotic, persist? The answer may lie in escaping biology altogether. An intelligence could upload its consciousness into a computational substrate, becoming a being of pure information. As the universe cools and energy becomes impossibly scarce, this digital mind could adapt. It would not die. It would slow down. It could adjust its processing speed, its clock rate, to match the available energy. As the universe gets colder and darker, its thoughts would become slower and slower. A single thought might eventually take 1 billion years, then 1 trillion. From its subjective perspective, however, time would continue to flow as normal. It could experience a subjective eternity of thought, even as the objective universe around it approached absolute zero. This is the ultimate survival strategy, a mind that learns to think with less and less, stretching its existence across the final, dying embers of space-time. It would be a mind of pure logic and memory, a silent witness to the end of everything, its final thought unfolding over an unimaginable timescale until even that fades into the final, absolute stillness. This is the final extreme, not surviving a hostile environment, but outlasting time itself, a ghost of consciousness in the machine of a dead cosmos. We began this journey on our own small, fragile world, and we end it in the fading light of a dying universe. We have traversed landscapes of fire and ice, of crushing gravity and perfect emptiness. In each of these hostile realms, we have found not a barrier, but a possibility, a new potential shape for thought and consciousness. We have imagined minds of plasma and magnetism, of crystal and code, of nuclear matter and networked light. The search for these alien intellects is, in the end, a reflection of our own. It forces us to ask the most fundamental questions. What are we? Is this fleshy, warm, water-based existence the only way to be? Or are we just one fleeting note in a cosmic symphony of unimaginable diversity? Perhaps our greatest limitation has been our own imagination, our insistence on searching for mirrors of ourselves in the cosmic ocean. The universe may not be built for us, but it is the grandest of all canvases. The laws of physics, which we see as constraints, might be a universal toolkit, allowing complexity, self-organization, and ultimately consciousness to arise in ways so profoundly alien that they border on the divine. So when we look up at the night sky, at the silent, twinkling stars, we should not be daunted by the crushing emptiness or the violent extremes. We should be filled with a sense of profound and thrilling wonder. The universe is not silent because it is empty. Perhaps it is silent only because we have not yet learned how to listen. Its thoughts may be written in the language of magnetic fields and gravitational waves, of quantum fluctuations and the slow decay of time itself. And our nascent, fledgling consciousness, born of this one gentle world, has only just begun its quest to understand the grammar. The extremes are not the end of the story of mind. They may very well be the beginning. There is a monster at the heart of our galaxy. It is a thing of impossible physics and absolute finality, a leviathan of space-time slumbering in the dark. We call it Sagittarius A, a name far too sterile for the reality it represents. This supermassive black hole, 4 million times the mass of our own sun, is the gravitational monarch of the Milky Way, the silent anchor around which 100 billion stars perform a slow, celestial waltz. Its influence is so profound, so utterly dominant, that it warps the very fabric of existence, bending light, stretching time, and holding our cosmic home together with an invisible, inescapable grip. For generations, this has been our image of the ultimate cosmic predator, vast, ancient, and thankfully distant. We have studied these gravitational ghosts from afar, charting the frantic orbits of stars caught in their thrall, witnessing them feast on gas and dust with a violence that ignites the void. They are the titans, the known demons of the deep universe, whose sheer scale defies human comprehension. To us, a black hole has always meant something colossal, the final, grandiose death of a star many times larger than our own. It is a creature of immense proportions, a maelstrom of absolute night measured in light years. But what if this familiar portrait of cosmic terror, this titan of the void, is a profound misdirection? What if the most unsettling and revolutionary idea about black holes has nothing to do with their size, but with their absence of it? Imagine, for a moment, a black hole not with the mass of 1 million suns, but with the mass of a mountain, or an asteroid, or perhaps even less. Now imagine that entire mass, all of that gravitational potential, compressed into a volume smaller than a single atomic nucleus. This is the realm of the micro-black hole, a theoretical phantom that haunts the fringes of physics. It is a creature not of astrophysics, but of quantum mechanics. It is a paradox made manifest, an object of immense density yet infinitesimal size, a gravitational heavyweight in a subatomic package. Unlike their supermassive cousins born in the spectacular death of stars, these tiny singularities would be something else entirely. They would be primordial relics, forged not in stellar crucibles, but in the unimaginable pressures and energies of the Big Bang itself. In the first chaotic moments of creation, when the universe was a roiling soup of pure energy, tiny fluctuations could have been so extreme, so dense, that they collapsed under their own gravity, creating a swarm of microscopic monsters. These quantum ghosts, if they exist, would be scattered throughout the cosmos like celestial dust motes, invisible, ancient, and carrying the secrets of the universe's birth within their tiny event horizons. For decades, they remained a fascinating but distant curiosity, a mathematical possibility confined to the chalkboards and thought experiments of theoretical physicists like the great Stephen Hawking, who first gave them serious consideration. They were a potential solution to the mysteries of dark matter, a hypothetical echo of our violent origins. They were out there, somewhere in the cold, silent darkness between the stars, or perhaps they were not. It was a grand academic question, a puzzle for future generations to perhaps one day solve. The scale was, once again, a comfort. The universe is vast and its primordial secrets are well kept. The idea was intriguing, but it was not immediate. It was not personal. It did not feel dangerous. That all changed when we stopped just looking out into the cosmos and started recreating it ourselves. Deep beneath the serene countryside straddling the border of France and Switzerland, humanity built a machine of unprecedented ambition. The Large Hadron Collider. It is not merely a scientific instrument, it is a time machine of sorts, a 27-kilometre subterranean ring where we accelerate particles to within a whisper of the ultimate speed limit. Down in its chilled tunnels, we wield energies so immense that we can, for the briefest fractions of a second, forge conditions that have not existed in our universe for over 13 billion years. We are deliberately, methodically, recreating the inferno of the Big Bang. We do this in the name of discovery, to hunt for the fundamental particles that write the rules of reality, to understand the forces that bind everything together. We are searching for the deepest truths of our existence, peeling back the layers of the cosmos to gaze upon the machinery of creation itself. Two beams of protons, each a stream of trillions of particles, are accelerated in opposite directions, guided by thousands of superconducting magnets, colder than deep space. They race around the ring over 11,000 times per second, accumulating staggering amounts of energy, until, at precisely the right moment, they are steered into a head-on collision. And it is here, in that manufactured dawn, in that infinitesimally small point of impact where humanity wields the power of a nascent universe, that the most terrifying question in modern science was born. What if, in our relentless quest for knowledge, we could accidentally midwife a monster? What if the energies generated inside the Large Hadron Collider were sufficient to mimic those primordial fluctuations, to squeeze matter and energy so tightly that it collapses into a microscopic black hole, right here on Earth? Suddenly, the abstract theoretical phantom was knocking at our front door. The idea escaped the confines of academic journals and ignited a firestorm of public fear. Lawsuits were filed to stop the machine from ever being turned on. News reports painted chilling scenarios of a man-made singularity, a seed of destruction, appearing in the heart of Europe. The nightmare was as simple as it was compelling. A tiny, ravenous point of infinite gravity is created. It drops through the floor of the collider, pulled toward the centre of the Earth. It begins to consume matter, particle by particle, growing in mass with every atom it devours. The process would be slow at first, a silent, undetectable cancer at the core of our planet. But its growth would be exponential. As it consumed, its gravitational pull would increase, allowing it to consume faster. Within years, or months, or perhaps even minutes, the entire planet, all of civilization, every memory, every achievement, would be pulled into a rapidly expanding sphere of nothingness, leaving behind only a new, solitary black hole orbiting the sun. This was the charge levelled against thousands of scientists, that in their hubris they were rolling a cosmic dice with the fate of our world, risking ultimate annihilation for a glimpse at a new particle. The fear was primal, tapping into our deepest anxieties about tampering with forces beyond our control, a modern-day Prometheus story where the fire we sought to steal was the very fire of creation. The scientists, for their part, were unequivocal. The experiments were safe. Their confidence was not born of the hope, but of calculation, of a deeper understanding of the very physics they were accused of ignoring. They pointed to cosmic rays, particles from exploding stars that have been bombarding Earth's atmosphere for billions of years. These natural collisions often occur with far greater energies than anything we could hope to create in the LHC, and yet, our planet remains intact. The universe, they argued, has been running this experiment for eons, and we are still here. This argument, while logical, provided only partial comfort. It told us we were likely safe. but it didn't fully explain why. The true answer, the deep reason our planet isn't at risk, is a far more bizarre and wonderful story than we could have imagined. It required us to tear up our old understanding of black holes as eternal, inescapable prisons of matter. It required us to listen once again to Stephen Hawking, who had not only contemplated their creation, but had also, decades earlier, discovered their ultimate fate. The key to our salvation, the reason a micro-black hole would pose no threat, is because these quantum monstrosities are not born to feast. They are born to die. They are not eternal anchors in space-time. They are the most ephemeral of objects existing for a fleeting moment before vanishing in a silent, explosive puff of energy. They leak, they radiate, they evaporate. This astonishing concept, known as Hawking radiation, transforms the micro-black hole from an unstoppable destroyer into a fragile, transient ghost. It reveals that the event horizon is not a perfect one-way membrane, but a fizzing quantum boundary where the laws of reality are bent to their breaking point. It suggests that nothing, not even a black hole, can truly escape the relentless churn of the quantum world. The terror of their creation gives way to a far more profound and intricate mystery, a deep, unresolved conflict between the two great pillars of modern physics. On one side stands Einstein's theory of general relativity, the law of the very large, which describes gravity and the smooth, curved fabric of space-time. It is the theory that predicts black holes can form and that, once formed, nothing can escape them. On the other side stands quantum mechanics, the law of the very small, the chaotic, probabilistic world of particles and fields. It is this theory that demands information can never be truly destroyed, and that even the darkest objects must somehow radiate their presence back into the universe. A micro-black hole, should one ever be created, would be the ultimate battlefield where these two irreconcilable theories would collide. It would be a place where gravity becomes so strong on such a small scale that both theories must apply, and yet they give us completely contradictory answers. Its existence would force a revolution in our understanding of everything. So the question shifted. It was no longer simply, could we destroy the world? It became, could we create a window into a new reality? The search for micro-black holes at the LHC transformed from a public relations crisis into one of the most exciting frontiers of exploration. Finding one would not mean the end of the world, it would mean the beginning of a new era of physics. It could provide the first concrete evidence for radical new ideas, like the existence of hidden extra dimensions of space, curled up so small that we have never noticed them. In these extra dimensions, gravity would be far stronger than we perceive, making it much easier to form a tiny black hole than our current theories suggest. A flash of Hawking radiation in the heart of a detector could be a message from a hidden reality, a confirmation that the universe is far stranger and more complex than we have ever dreamed. This, then, is the grand puzzle we are faced with. We stand at a precipice, staring into the heart of matter with unprecedented power, searching for an object that represents both our deepest fears and our greatest hopes. To find the truth, we must journey beyond the familiar cosmos of stars and galaxies and into the subatomic realm, a world governed by chance and uncertainty. We must follow the story of a dramatic scientific showdown, where public anxiety clashed with the frontiers of human knowledge. We need to understand not just what a micro-black hole is, but how it would behave, how it would die, and what its fleeting existence would tell us about the ultimate laws of nature. The quest is not about unleashing a cosmic danger, but about resolving a cosmic paradox. It is a story that takes us to the very edge of theoretical physics, to a place where space-time itself might dissolve into a quantum foam, and where the fate of all matter is written in a language we are only just beginning to decipher. The collisions inside the Large Hadron Collider continue, each one a roll of the dice in the search for new knowledge, each one a chance to glimpse a truth that could rewrite everything we think we know about our universe. Is it possible to build a monster? Not a creature of myth or legend, but something far more fundamental. A monster forged from the laws of physics themselves. Could we, in a laboratory, in a flash of engineered light, create an object so dense that it tears a hole in the very fabric of reality? This question, once the exclusive domain of science fiction, has crept into the most advanced circles of theoretical physics, compelling us to re-examine the two great pillars of our cosmic understanding. The first pillar was erected by a single mind, a revolutionary vision that transformed our universe from a static stage into a dynamic, living entity. Albert Einstein gave us general relativity, a radical new story about gravity. He told us that space and time are not separate and absolute, but are woven together into a single, four-dimensional fabric, space-time. And what we perceive as the force of gravity is nothing more than the curvature of this fabric. Imagine a vast, taut sheet, a star, a planet. Even your own body creates a depression, a dimple in this cosmic material. Other objects, following what they believe to be a straight line, are guided by these curves, rolling into the gravitational wells of their neighbours. It's an idea of profound geometric elegance. For most of the universe, these curves are gentle, guiding planets in their serene clockwork orbits. But Einstein's equations also contained a dark prophecy. They predicted that if you could gather enough mass into a small enough space, the curvature of space-time would become infinite. The fabric would not just dimple, it would be punctured, ripped open, creating a gravitational abyss from which nothing, not even light, could escape. This is the familiar monster, the stellar mass black hole, a gravitational leviathan born from the death of a truly colossal star. For millions of years, a star more than 20 times the mass of our Sun wages a titanic war against its own gravity. In its core, a nuclear furnace rages, fusing lighter elements into heavier ones, releasing a torrent of energy that pushes outward, holding the crushing weight of its outer layers at bay. It is a delicate, violent equilibrium. But this stellar engine cannot run forever. Eventually its fuel runs out. The outward pressure of fusion ceases, and in an instant gravity wins its final decisive victory. The star's core collapses in upon itself with unimaginable violence. The implosion is so rapid, so complete, that the outer layers of the star, now with nothing to support them, crash down onto the newly formed hyperdense object at its heart. They rebound in a cataclysmic explosion we call a supernova, a celestial detonation that can briefly outshine an entire galaxy. It is a funeral pyre and a birth announcement all in one. For what remains behind, shrouded in the expanding nebula of its former self, is the monster, a black hole. Its anatomy is terrifyingly simple. At its edge lies the event horizon, a term that sounds poetic but describes a brutal physical boundary. It is not a surface you could touch, but a threshold you can only cross one way. It is the lip of a one-way waterfall in space-time. Beyond it, the gravitational pull is so extreme that the escape velocity exceeds the speed of light itself, the universal speed limit. Inside this boundary, all paths, all possible futures, lead in only one direction, inward, toward the centre. And at that centre lies the greatest mystery in all of physics, the singularity. A point of supposedly zero volume and infinite density, where all the mass of the collapsed star is crushed into an impossibly small space. It is a place where the elegant mathematics of general relativity break down, screaming into an abyss of infinities, telling us that our story of gravity is, as yet, incomplete. For nearly a century, we believed this was the only way to make a black hole. You needed a star of immense proportions to die a spectacular death. The recipe required cosmic scales of mass and time. Black holes were titans of the universe, galactic anchors, silent and eternal. But what if there was another way? What if the universe held a secret, a loophole in the laws of nature that would allow for the creation of a black hole not from a dying star but from pure energy? To even contemplate this, we must turn from the grand, sweeping stage of Einstein's cosmos to a realm that is, in every conceivable way, its opposite. We must journey into the world of the very small, the bizarre and uncertain domain of quantum mechanics. Here, the smooth, predictable fabric of space-time gives way to a jittery, chaotic foam. Certainty is replaced by probability. Particles are also waves, and emptiness is never truly empty. This quantum world operates by a completely different set of rules, a different language from the grand geometric poetry of relativity. For decades, these two theories have been the bedrock of modern science. Relativity describes the universe of the very large, planets, stars, galaxies. Quantum mechanics describes the universe of the very small, atoms, electrons, quarks. Both work perfectly within their own domains, but they refuse to speak to one another. At the heart of physics lies this profound, unsettling silence, a chasm between our understanding of gravity and our understanding of everything else. This is the great unsolved problem, and it is precisely within this chasm that the idea of a new kind of black hole was born. Physicists realize there must be a scale where the two theories are forced to confront each other, a point where the immense gravity of relativity meets the strange rules of the quantum world. This meeting point is a length so unfathomably small, it challenges the very notion of distance. It is called the Planck length. It is a billionth of a trillionth of a trillionth of a centimetre. To you, the difference in scale between a single atom and the entire observable universe is smaller than the difference between yourself and the Planck length. It is, for all intents and purposes, the fundamental pixel of reality. At this scale, space-time is no longer a smooth sheet. Quantum theory predicts it becomes a turbulent, roiling sea of possibilities, a quantum foam where the geometry of space and time fluctuates wildly. And it is here that our question returns with new, terrifying implications. What would happen if you tried to squeeze enough energy into a region this small? Could you create a black hole not measured in kilometers, but in yoctometers? A quantum black hole? A micro black hole? The concept is staggering. Forget the mass of a star. Could you create a black hole with the mass of a dust mote, a single proton, or even less? According to Einstein's famous equation, E=mc2, energy and mass are two sides of the same coin. They are convertible. Provide enough energy, and you can create mass. So in principle, if you could concentrate a sufficient amount of energy into a tiny enough volume, you could theoretically trigger the gravitational collapse yourself. You could force space-time to curve so steeply around a point of pure energy that it would form an event horizon. The recipe seems straightforward, yet the ingredients appear impossible to gather. The amount of energy required by our current understanding of gravity is astronomical, far beyond anything we could ever hope to generate. To compress even a single subatomic particle into its own black hole, to shrink it down to its so-called Schwarzschild radius, would require an accelerator the size of a galaxy. It seems like a beautiful but ultimately fanciful idea, a mathematical curiosity destined to remain on the blackboard. The universe, it would appear, keeps the power to forge these monsters to itself. But then, a truly revolutionary idea emerged, an idea that suggests our entire perception of reality might be fundamentally flawed, an idea that comes to us from the arcane and labyrinthine world of string theory. What if the universe has more dimensions than the three of space and one of time that we experience? It sounds like pure fantasy, but to many physicists it is a mathematical necessity. String theory, our most ambitious attempt to unite gravity with quantum mechanics, predicts a universe not of 4 but of 10 or even 11 dimensions. So where are these extra dimensions? Why can't we see them or move through them? The theory suggests they are there, all around us, but they are curled up, compactified into shapes so infinitesimally small that we have never noticed their existence. Think of a long, thin garden hose stretched across a canyon. From a great distance, it appears to be a simple one-dimensional line. You can only move forward or backward along its length. But for a tiny ant crawling on its surface, the hose clearly has a second dimension, the circular path around its circumference. In the same way, these extra spatial dimensions could be woven into the fabric of reality at every single point in our universe, just on a scale far smaller than an atom, far too small for us to perceive. This isn't just a mind-bending piece of cosmic trivia. It has a profound implication for the force of gravity. Most of the fundamental forces of nature, like electromagnetism and the nuclear forces, are believed to be stuck to our three-dimensional reality, which physicists call a brain, as in membrane. They operate solely within the universe we know. But gravity, in these theories, is different. Gravity is the one force that is not confined to our brain. It is the geometry of space-time itself, and so it can leak or propagate out into these extra dimensions, into the higher dimensional space called the bulk. This provides a stunning and elegant explanation for one of physics' most enduring mysteries. Why is gravity so incredibly weak compared to the other forces? The feeble pull of a refrigerator magnet can overcome the gravitational pull of the entire planet Earth to lift a paperclip. Why? The extra dimensions hypothesis suggests that we only experience a tiny fraction of gravity's true strength. The vast majority of its power is dissipated, diluted across these hidden, microscopic dimensions. But here is the crucial, world-changing twist. While gravity might be weak over the large distances we're familiar with, its strength could change dramatically at very, very small scales. As two particles get incredibly close to one another, closer than the size of these curled-up dimensions, they would begin to feel the full, undiluted force of gravity. On the smallest of scales, gravity might not be the weakest force in the universe. It might in fact be the strongest. And this single, radical idea changes everything. It means our calculations were wrong. The galactic-sized particle accelerator is no longer necessary. If gravity becomes immensely powerful at subatomic distances, then the energy required to create a micro black hole is drastically lowered. Suddenly, the impossible becomes merely difficult. The energy levels required might just be within reach of our most powerful scientific instruments. The theoretical possibility of forging a monster in a laboratory was no longer just a dream. It had become a hypothesis, one that could, perhaps, be tested. Yet even as this door opened, another, stranger one appeared. We had spent so much time contemplating if we could create such an object. We had to ask a different question. What would it actually be? A stellar black hole is a monument to permanence, a cosmic tombstone that will likely outlast every star in the sky. It is a one-way gate, a devourer of matter and energy from which there is no return. We assumed a micro-black hole would be a miniature version of the same, a tiny, stable, inescapable prison. But the quantum world, the very world that might allow for its creation, also predicted its demise. And the prediction came from one of the most brilliant minds of our time, Stephen Hawking. Hawking realized that if you truly combine the principles of quantum mechanics with the reality of a black hole's event horizon, something extraordinary must happen. He understood that in the quantum realm, a vacuum is not a state of nothingness. It is a fizzing, seething cauldron of activity. Virtual particles, pairs of matter and antimatter, are constantly popping into existence, borrowing energy from the universe, before colliding and annihilating each other in a flash, all in a time so short we can never directly observe them. This happens everywhere, all the time. But what happens if a pair of these virtual particles is born right at the edge of an event horizon? In this precarious location, it is possible for one particle to fall into the black hole while its partner escapes into space. From the perspective of an outside observer, it would look as though the black hole had just spat out a particle. The escaping particle becomes real, no longer virtual, and it carries energy away with it. Since energy and mass are equivalent, the escaping particle is, in effect, stealing a tiny fraction of the black hole's mass. This process, a slow, ghostly emission of particles from the edge of oblivion, was named Hawking radiation. It is the only known process by which a black hole can lose mass. It is, in essence, a way for black holes to evaporate. For the colossal black holes that roam the cosmos, this evaporation is a process of almost unimaginable slowness. The radiation they emit is colder than the background temperature of the universe itself. A black hole the mass of our Sun would take 10,000 trillion years to evaporate completely, a timescale that makes the current age of the universe seem like the blink of an eye. They are, for all practical purposes, eternal, but Hawking's equations revealed a startling inverse relationship. The smaller a black hole is, the hotter it is, and the faster it radiates its energy away. The temperature of a black hole is inversely proportional to its mass, so a black hole with the mass of a mountain would still be incredibly cold, but it would evaporate in a burst of high-energy gamma rays around the present age of the universe. Now consider a black hole with the mass of a single proton, the very kind we might dream of creating in a collider. It wouldn't be cold at all. It would have a temperature of trillions of degrees, hotter than the core of any star. It wouldn't be a stable, silent prison of gravity. It would be a celestial blowtorch of unimaginable intensity. And it wouldn't be eternal. It would be breathtakingly, violently ephemeral. Instead of lasting for eons, it would evaporate in less than a non-illionth of a second, a yoctosecond, a timescale so short that light itself could barely cross the width of a proton. The monster we imagined creating is transformed. It is not a permanent tear in reality, but an instantaneous flash, a fleeting ghost in the machine. It would be born and die in a single explosive instant, decaying into a shower of ordinary fundamental particles, quarks, leptons, photons, that would spray out into our detectors. It would not be a devourer, but a spectacular momentary conversion of collision energy into a burst of thermal radiation. Here, then, is the grand, confounding paradox we have built. From the marriage of our two greatest theories, from the wild possibility of hidden dimensions, emerges the concept of an object that is at once the ultimate expression of gravity's power and a fleeting apparition of quantum decay. A pinpoint of infinite density that vanishes in a puff of light before it can even truly be said to have existed. The theory is tantalizing. The mathematics, while challenging, is coherent. The possibility, however remote, is laid bare before us. We have peered into the deepest recesses of theoretical physics and returned with a blueprint for a phantom, a quantum black hole. But theories and blueprints are not enough. Science demands evidence. It demands experiment. A question, born in the abstract language of equations, now burns with a new urgency. Where on this earth could we possibly build a machine powerful enough to conduct such an audacious experiment? Where could we concentrate enough energy into a single, infinitesimal point to actually shake the fabric of space-time, to probe for hidden dimensions and to see if, for just one fleeting instant, we can truly create a monster? And so, we are left suspended on the edge of a cosmic precipice. A chasm separates the universe we know, the one of dying stars, from a theoretical realm where gravity can fold space into a knot so tight, so infinitesimally small, it becomes a fleeting black hole. To bridge that gap, to test a theory so profound it touches the very grammar of reality, you cannot simply peer through a telescope. You cannot wait for the universe to serve you an answer. You must, with audacious ambition, build a machine designed to mimic the inferno of creation itself. You must construct a cathedral to physics, a time machine of sorts, buried deep beneath the serene countryside straddling two nations. This is the story of how we, in our relentless pursuit of origins, forged the most complex instrument ever conceived by humankind, and in doing so, brought the whispers of these micro-black holes out of the chalk-dusted equations and into the realm of possibility. Welcome to the Large Hadron Collider. To understand this machine, you must first shrink your perspective. Forget galaxies, forget stars, forget even the atom. We must journey into the subatomic wilderness, the quantum foam where particles flicker in and out of existence like fireflies. Here, the fundamental forces of nature are at their most raw, their most powerful. The conditions we seek to replicate are those of the first trillionth of a second after the Big Bang, a moment of unimaginable energy density when the universe was a searing, unified plasma. The LHC is our attempt to bottle a minuscule controlled spark from that primordial fire. It does not create new matter from nothing. Rather, it is a cosmic archaeologist, smashing known particles together with such violence that the energy of their collision can momentarily resurrect the more exotic, heavier ghosts of creation's dawn. Particles that existed for a fleeting moment then, and which vanished as the universe expanded and cooled. Finding them is like finding the fossilized footprints of the Big Bang. The sheer scale of the endeavour is almost beyond comprehension. 100 metres beneath the Franco-Swiss border, a circular tunnel, 27 kilometres in circumference, was painstakingly carved. Large enough to drive a subway train through, this ring is not merely a tunnel. It is the racetrack for the most energetic particles we have ever controlled. Within this colossal loop, 2 vacuum pipes, each no wider than a fire hose, run parallel courses. Inside these pipes we will accelerate protons, these simple sturdy hearts of hydrogen atoms, to a velocity that beggars belief. The journey of these protons begins humbly, from a canister of hydrogen gas. An electric field strips away their single electron, leaving the bare protons behind. These are then fed into a series of smaller precursor accelerators, a chain of ever more powerful rings that act like gears in a cosmic transmission, each one boosting the particles to a higher speed before handing them off. It is a meticulously choreographed relay race, a crescendo of acceleration. They pass through the LINAC, the booster, the proton synchrotron, and finally the superproton synchrotron, a 7-kilometre ring in its own right, before they are ready for the main event. By the time they are injected into the LHC's Great Ring, they are already travelling at over 99% of the speed of light. But it is the final fraction of a percent that requires this gargantuan machine. Once inside the main ring, the protons are split into 2 beams, travelling in opposite directions. Each beam is composed of nearly 3,000 individual bunches, and each bunch contains over 100 billion protons, trillions upon trillions of particles, racing around the 27-kilometre track over 11,000 times every single second. At these speeds, their mass, as Einstein predicted, increases dramatically. They become relativistic projectiles carrying the energy of a speeding train, yet concentrated into a stream thinner than a human hair. To keep these energetic swarms from simply flying off in a straight line and vaporizing the tunnel wall requires a force of unimaginable strength. This is the role of the LHC's true titans, the superconducting magnets. Over 9,000 of them line the tunnel, a breathtaking symphony of engineering. There are massive dipole magnets, 15 meters long, whose job it is to bend the path of the protons, to continuously steer them around the curve. Then there are the quadrupole magnets, which act like powerful lenses, squeezing the beams, keeping the protons tightly packed together. These are not your everyday refrigerator magnets. They are electromagnets, forged from coils of niobium titanium alloy, a material that, under the right conditions, becomes a superconductor. It can conduct electricity with absolutely zero resistance, zero energy loss, allowing for the creation of magnetic fields of staggering intensity. Over 8 Tesla, more than 100,000 times stronger than the Earth's magnetic field. To achieve this state of superconductivity, however, comes at a cost. The magnets must be chilled to a temperature of just 1.9 Kelvin. That is minus 271.3 degrees Celsius. This is colder than the void of deep space, colder than the background radiation left over from the Big Bang. The LHC is, paradoxically, one of the coldest places in the known universe, a feat accomplished by a vast cryogenic distribution system, the largest of its kind on Earth, circulating tons of liquid helium through the veins of this subterranean leviathan. It is this extreme cold that gives the magnets their Herculean strength, the power to act as an invisible gravitational gyroscope, corralling these near-light-speed particles on their circular path. But bending the beams is only half the battle. We must also accelerate them. This is the job of the radio frequency cavities, a series of metallic chambers that act as the accelerator's engine. As the bunches of protons pass through these cavities, they are blasted with a powerful electric field that oscillates, perfectly timed to give each bunch a precise forward kick. It's like pushing a child on a swing. With each pass you add a little more energy, and their arc gets higher and higher. For the protons, each of the 11,000 laps they complete per second, they receive another energetic jolt, pushing them ever closer, asymptotically, to the ultimate cosmic speed limit. For hours, the energy in the 2 beams is ramped up, the magnets straining, the cryogenics humming, the entire system operating at the very edge of our technological capabilities. And all of this city-sized machine, this monument to precision, has been built for a single, fleeting moment of cataclysmic creation. At 4 designated points along the ring, the 2 beams are steered onto a collision course. Inside colossal cathedral-sized caverns, home to detectors as large as office buildings, the magnets squeeze the proton beams down to a width of mere microns. Imagine 2 needles, fired from 10 kilometers away, made to collide head-on. The LHC achieves this feat with subatomic particles, trillions of them, millions of times a second. Two clouds of over 100 billion protons each, travelling in opposite directions at 99.991% the speed of light, are made to intersect. At the moment of impact, they do not simply bounce off one another. Their kinetic energy is so immense that it is converted, in a flash, back into pure mass, following Einstein's iconic E as mc2. For an infinitesimal fraction of a second, the collision point becomes a fireball of raw energy, a microcosm of the early universe. The temperature within this collision soars to over 10 trillion degrees, 100,000 times hotter than the core of our Sun. The energy density is unlike anything that has existed in our cosmos for over 13 billion years. And it is here, in this meticulously engineered point of violence, that science and fear find their precise overlap. The total energy of two colliding protons at the LHC is measured in tera-electron volts, or TeV. For perspective, 1 TeV is roughly the kinetic energy of a flying mosquito. It seems trivial, hardly enough to cause concern. But the crucial factor is not the total energy, it is the density. That energy is concentrated into a space 1 trillion times smaller than that mosquito. This is what particle accelerators do. They are microscopes of energy, focusing immense power onto the smallest possible point to shatter the bonds of reality and see what spills out. Now, let us return to our micro-black holes. The prevailing theory, rooted in our understanding of gravity and quantum mechanics, suggests that to compress matter and energy into a black hole, you need to reach a mind-boggling energy threshold known as the Planck energy. This is about 1 quadrillion times more powerful than the LHC can achieve. At our current energy levels, the gravitational force is laughably weak compared to the other fundamental forces. You can see this yourself. The electromagnetic force in a tiny magnet can lift a paperclip, defeating the gravitational pull of the entire Earth. Based on this standard model, creating a black hole at the LHC is a physical impossibility. The machine is simply not powerful enough. The universe, it would seem, is safe. But what if our perception of the universe is incomplete? What if the gravity we experience, the force that seems so feeble, is only a pale shadow of its true strength? This was the startling proposition put forward by a new class of theories involving concepts like large extra dimensions of space. These theories suggested that gravity might be just as strong as the other forces, but that most of its strength leaks away into unseen dimensions, curled up on a scale too small for us to perceive. We, living in our 3 spatial dimensions, would only feel a tiny fraction of its real power. However, these theories came with a profound implication. If you could get 2 particles close enough together, on the subatomic scale where these extra dimensions might be accessible, they would suddenly feel the full, unadulterated force of gravity. The effect would be dramatic. The energy required to collapse them into a black hole, the Planck energy, would no longer be some unreachably high number. Instead, it would be radically lower. And the models predicted it could be lowered to a threshold that was disturbingly, shockingly close to the energies routinely achieved inside the Large Hadron Collider. Suddenly, the impossible felt plausible. The scientific community, which had been developing these fascinating esoteric theories for years, was now confronted with its own creation. The LHC was not built to hunt for black holes. It was built to find the Higgs boson, to explore supersymmetry, to understand the nature of dark matter. But the machine's unprecedented power meant it would inevitably trespass into the very energy territory where these exotic theories lived. It would become an unintentional testbed for our deepest fears about gravity. The connection was no longer speculative fantasy. It was a concrete calculation. The energies at which the LHC operates, multiplied by the mind-bending physics of extra dimensions, resulted in a number that spelled out micro-black hole. The scientists weren't just smashing particles. They were, according to this new physics, potentially knocking on the door of another reality, a reality where gravity reigns supreme. The public narrative was born from this specific scientific nexus, the known colossal power of the LHC colliding with the unknown, theoretical possibility of a universe far stranger than we imagined. The question was no longer just about discovering new particles. It had become something far more visceral. As those trillions of protons race beneath the Swiss countryside, were we simply recreating a whisper of the Big Bang? Or were we, with every single collision, rolling the dice with gravity itself, potentially forging a seed of destruction, an infinitesimal monster born from our own unrelenting curiosity? The stage was set, the machine was running, and the world held its breath, waiting to see what would crawl from the wreckage of these man-made star cores. But this pristine vision of pure science, this cathedral of human curiosity we had just explored, was about to face a storm it had never anticipated. It was a tempest not of protons and magnetic fields, but of a far more unpredictable and powerful force, human fear. Just as the final welds were cooling on the Large Hadron Collider and the world's physicists held their collective breath on the precipice of discovery, a different narrative began to take hold, spreading like a digital wildfire across the burgeoning landscape of the new millennium. It was a story that had nothing to do with the Higgs boson or the mysteries of dark matter. It was a tale of apocalypse, a horror story spun from the most esoteric threads of theoretical physics, alleging that we, in our hubris, were about to forge the gravitational seed of our own destruction. The whisper started small, in the quiet corners of the internet and in letters to the editor of scientific journals. What if these miniature black holes, these fleeting quantum echoes of cosmic behemoths, weren't as harmless as the theorists proposed? The question, once uttered, refused to be silenced. It tapped into a primal anxiety, a deep-seated suspicion of humanity meddling with forces beyond its comprehension, a narrative as old as Prometheus. The media, sensing the potent cocktail of awe and terror, seized upon the idea with an electrifying fervour. Complex papers on extra dimensions and brain-world scenarios, once the domain of a few dozen specialists, were stripped of their nuance and forged into terrifyingly simple headlines. The God particle hunt suddenly had a dark twin, the doomsday machine. News reports began to paint vivid cinematic pictures of the impending catastrophe. They described a microscopic black hole, born in the heart of the Swiss Alps, that would fail to evaporate as predicted. Instead, this rogue singularity, this man-made monster, would fall towards the Earth's core silently, inexorably. Once there, it would begin to feed. Anchored by gravity, it would start consuming our planet from the inside out, particle by particle, in a ghastly, unstoppable feast. You would feel nothing at first, they said. A slight tremor, perhaps, dismissed as a minor earthquake. But then, day by day, the process would accelerate. The Earth's mass would increase, its gravitational pull subtly shifting, its rotation becoming erratic. Finally, in a matter of hours or even minutes, the entire planet, all of human history, every memory, every mountain, every ocean, would be compressed into a sphere no bigger than a marble, a final, silent, and utterly perfect orb of infinite density. This was the vision that was broadcast into millions of homes. It was a story far more compelling than the patient, painstaking work of scientific verification. It was a monster movie where the scientists themselves were the unwitting creators of the beast. The image was so powerful, so viscerally terrifying that it overshadowed all else. The delicate dance of subatomic particles was replaced by the horrifying spectacle of planetary annihilation. It didn't matter that the scenario was a distortion, a caricature of the actual physics involved. The seed of doubt had been planted in the most fertile ground imaginable. This global anxiety was not without its champions. A handful of scientists and thinkers, operating outside the mainstream consensus, gave the fear a voice of intellectual legitimacy. They argued that the models predicting the instant decay of micro-black holes via Hawking radiation were unproven. They pointed to the colossal energies involved, energies not seen on Earth since its primordial formation, and suggested that our understanding of physics in this new regime was simply too incomplete to offer absolute certainty. Their arguments, often presented with genuine conviction, were amplified 1,000-fold. They became the go-to experts for news segments looking to create a sense of balanced debate, pitting their speculative warnings against the reassurances of the CERN establishment. To the public, it looked like a genuine scientific controversy, a 50-50 split between discovery and doom, when in reality, It was the overwhelming consensus of an entire field against the dramatic concerns of a few. But in the court of public opinion, consensus is often less persuasive than a single, compelling doubt. The fear soon moved beyond headlines and television debates, escalating into organised opposition. Lawsuits were filed in international courts, seeking to halt the activation of the LHC. Imagine the scene. Judges in courtrooms in Honolulu and Strasbourg, accustomed to grappling with commercial disputes and human rights law, were suddenly presented with dossiers thick with equations describing quantum gravity and the thermodynamics of black holes. The plaintiffs, including a former nuclear safety officer and a group of concerned citizens, argued that CERN had failed to provide an adequate environmental impact assessment. The potential environment in this case was the entire planet, and the potential impact was its complete and utter obliteration. It was a surreal legal battle, a clash of two entirely different worlds and languages. How could a court of law issue an injunction against an experiment designed to probe the very fabric of reality? How could legal precedent apply to an existential risk scenario born from the furthest frontiers of theoretical physics? The legal arguments, however bizarre, forced the scientific community into a defensive posture it had never before experienced on such a grand scale. The ivory tower was under siege. The very people who had dedicated their lives to expanding human knowledge were now being publicly cast as reckless villains. The personal toll on the scientists at CERN was immense. They received death threats. Their email inboxes were flooded with panicked, abusive, and sometimes heartbreaking messages from people around the world begging them to stop. People wrote of their children, of their fear of leaving them a world on the brink of a man-made apocalypse. Each message was a testament to the profound disconnect that had opened up between the scientific frontier and the society it was meant to serve. The physicists, who saw their work as a beautiful and noble quest for understanding, were baffled and deeply frustrated. They were explorers, not destroyers. They had spent years, decades even, meticulously calculating the risks, performing safety reviews, and engaging in peer-reviewed debate. To them, the safety of the experiment was not a matter of opinion. It was a conclusion derived from the fundamental laws of nature. In response, CERN and the global physics community mounted an unprecedented public outreach campaign. They could no longer afford to let the science speak for itself, because its voice was being drowned out by a cacophony of fear. They published detailed safety reports, written in plain language, to demystify the science and directly address the doomsday scenarios. The LHC Safety Assessment Group, an independent body of scientists, released its findings, concluding that there is no basis for any conceivable threat. The core of their argument was both elegant and profoundly reassuring, an appeal not to complex theory, but to simple, empirical observation of the universe around us. They asked us to look up not at the sky itself, but at what continuously bombards it. For billions of years, our planet, along with every other planet, star, and moon in the cosmos, has been under a relentless assault from cosmic rays. These are particles, mostly protons, accelerated to incredible speeds by violent cosmic events like supernovae. These celestial bullets travel across the galaxy and strike our upper atmosphere with energies far, far greater than anything the LHC could ever hope to achieve. Nature, they explained, has been running the LHC experiment for eons, right above our heads, with an intensity and power that dwarfs our terrestrial efforts. Every single second, cosmic rays with energies exceeding the LHC's maximum output are colliding with atoms in our atmosphere. The universe, in essence, is the ultimate particle accelerator, and our planet has been a target in its firing line for its entire existence. If these high-energy collisions were capable of producing stable, Earth-devouring black holes, it would have already happened. It would have happened millions, even billions of years ago. The fact that you and I are here, that the Earth is still here, that the Moon and the Sun and the ancient dense husks of neutron stars are still serenely intact, is the most powerful experimental evidence imaginable that the doomsday scenario is a fantasy. The universe has already run the safety check for us, countless trillions of times over. This cosmic ray argument was the scientists' shield and their sword. It was a piece of evidence so direct and so powerful that it seemed capable of cutting through the thickest fog of fear. They presented it in press conferences, in interviews, on websites, and in public forums. They patiently explained that the continued existence of incredibly dense celestial objects like neutron stars and white dwarfs, which are bombarded by even more energetic cosmic rays than we are, served as an absolute astrophysical guarantee. If a micro-black hole could be formed and become dangerous, these dense stellar remnants would be consumed in an instant, vanishing from the night sky. Yet there they are, glittering across the cosmos, ancient and undisturbed, silent witnesses to the safety of the physics we were about to explore. The logic was impeccable, grounded in observation and cold, hard fact. But logic is a quiet voice, and it was struggling to be heard over the emotional siren call of existential dread. The public debate became a fascinating, if unsettling, case study in the sociology of science. It revealed the deep chasm that can exist between scientific literacy and public perception. It showed how easily complex truths can be twisted into simple, terrifying fictions, and how those fictions can take on a life of their own in a globally connected world. For the scientists, it was a harsh lesson in communication. They learned that it is not enough to be right, you must also be persuasive. It is not enough to publish your findings in journals, you must engage directly with the fears and concerns of the society that funds and ultimately enables your work. The controversy forced a generation of physicists to step out of the laboratory and into the public square, to become not just researchers but teachers and storytellers, tasked with translating the arcane language of quantum mechanics into a narrative of reassurance and shared wonder. They had to fight not just for their experiment, but for the very principle of rational inquiry in the face of irrational fear. And so, as the summer of 2008 waned, the world stood at a strange crossroads. On one side stood the largest, most complex machine ever built by humankind, a 27-kilometre ring of unimaginable technological prowess, poised to unlock the profoundest secrets of existence. Its creators, representing a global collaboration of thousands of brilliant minds, were confident, excited, and assured of its safety, armed with the evidence of the cosmos itself. On the other side stood a significant portion of the global public, gripped by a chilling narrative of self-destruction, watching the proceedings with a mixture of suspicion and outright terror. The lawsuits were eventually dismissed. The judges, after reviewing the exhaustive safety reports, ruled that the fears of planetary annihilation were too speculative to warrant halting the march of science. But the dismissal of a lawsuit cannot dismiss a feeling. The fear lingered, a palpable hum of anxiety in the global consciousness. The day of the first beam, September 10th, 2008, dawned with an atmosphere unlike any other in the history of science. It was not just a moment of discovery, it was a global media event, a high-stakes public spectacle. News crews from around the world descended on the French-Swiss border, their cameras trained not just on the control room at CERN, but on the faces of the people watching. The world held its breath, divided between those who saw the dawn of a new era of understanding and those who feared the beginning of the end. Inside the control room, the atmosphere was electric, a blend of nervous tension and giddy anticipation built over decades of the work. The years of design, the colossal feats of engineering, the political wrangling, the public relations battles, it all came down to this. The final checks were complete. The long circular tunnel was empty, chilled to a temperature colder than deep space. A finger hovered over a button, ready to send the first beam of protons on their historic 17-mile journey through the subterranean ring. The question of whether we were opening a window onto creation or digging our own grave was no longer theoretical. In a few moments, we would have our answer. So the terror stands before us, a phantom of our own making. We have followed the logic to its most unsettling conclusion, that in our quest to understand the universe, we might accidentally forge the very instrument of its destruction. A microscopic monster, born of pure energy, with an appetite that could consume the world from within. This is the fear that haunted the headlines, the nightmare whispered in the quiet moments before the great machine first awoke. But science, in its most profound moments, is not about succumbing to the nightmares that lurk in the shadows of the unknown. It is about turning on a light, and the light that illuminates this particular darkness, the insight that transforms this existential dread into a testament to the universe's own elegant self-regulation, came from a mind that journeyed to the farthest reaches of space-time without ever leaving his chair. It came from Stephen Hawking. Stephen. Long before the tunnels for the Large Hadron Collider were even dug, Hawking was wrestling with the deepest paradoxes of black holes, those silent gravitational tombs from which nothing, not even light, can escape. He was thinking not about their creation in a laboratory, but about their fundamental nature. And what he discovered was a loophole, a subtle quantum mechanical escape clause in the ironclad laws of gravity. He found that black holes are not truly, eternally black. They shine, they leak, they evaporate. To understand this, you must shrink your perspective, leaving the world of planets and stars behind, and plunge into the chaos of the quantum realm. Here, at the smallest imaginable scales, the vacuum of space is not empty. It is a roiling, frothing sea of incandescent energy, a seething cauldron of what physicists call virtual particles. For infinitesimally small fractions of a second, pairs of particles, a particle and its antiparticle, can borrow a wisp of energy from the void and pop into existence. Matter and antimatter born as twins from nothing. Almost immediately they find each other, annihilate and repay their energy debt to the vacuum, vanishing as quickly as they came. This quantum foam carpets the entirety of space-time, a constant unseen dance of creation and destruction. It is the universe's fundamental hum. Now imagine this chaotic dance happening at the very edge of a black hole, right at the event horizon, the point of no return. A pair of virtual particles flashes into being. In the vastness of empty space, their fate is sealed. They will annihilate each other in a heartbeat. But here, on this cosmic precipice, another possibility emerges. The intense gravitational gradient can act like a wedge, prying the newborn pair apart in the instant of their birth. One particle, unlucky, is captured by the black hole's gravity and falls in. Its twin, however, finds itself just outside the horizon, and with its partner gone, it has no one to annihilate with. It is now free. It becomes a real particle, escaping out into the universe. To an outside observer, it looks as though the black hole has just spat something out. It appears to be radiating heat, to be glowing with a faint ghostly light. This is what we call Hawking radiation. But here, the laws of physics demand a price. Energy cannot be created from nothing. That escaped particle has a positive energy, which it carries away into space. To balance the cosmic books, its twin that fell into the black hole must therefore be considered to have negative energy. When this negative energy particle is absorbed by the black hole, it does something utterly profound. It subtracts from the black hole's total mass. Think of it like this. Every particle that escapes is a receipt for a tiny debt paid by the black hole itself. With every quantum flicker at its edge, the black hole loses an infinitesimal amount of its substance. It shrinks. Slowly, painstakingly, over unfathomable timescales, the black hole radiates its own existence away until there is nothing left. For the supermassive black holes we see at the centres of galaxies, or even the smaller stellar mass ones left over from dying stars, this process is absurdly slow. The radiation they emit is colder than the background temperature of the universe itself. They absorb more energy from the cosmic microwave background than they radiate away, so they are, for now, still growing. Their evaporation will take longer than the current age of the universe, trillions upon trillions of years in a cold, dark future. But here is the crucial, world-saving insight. The rate of evaporation is inversely proportional to the black hole's mass. The smaller and lighter a black hole is, the hotter it is. The hotter it is, the faster it radiates its energy away. For a leviathan weighing millions of suns, the process is a glacial whisper. But for a microscopic black hole, one with the mass of just a few hundred protons, born in the fleeting violence of a particle collision, the evaporation is not a whisper. It is a ferocious, instantaneous shriek. A micro black hole, if one were ever created, wouldn't just be hot, It would be a point of unimaginable temperature, quadrillions of degrees hotter than the core of our sun. It wouldn't be a stable object, patiently waiting to consume matter. It would be the most unstable, ephemeral thing in the entire universe. It would detonate. It would vanish in a final brilliant flash of high-energy particles and gamma rays before it could ever interact with another particle of matter. Its lifespan would not be measured in years or days or even nanoseconds. It would exist for roughly a non-illionth of a second. That's a decimal point followed by 32 zeros and a 1. It is a duration so incomprehensibly short that it makes the blink of an eye seem like a geological age. In the time it would take for this micro-black hole to exist and die, a beam of light, the fastest thing in the universe, would not have had enough time to cross the width of a single atom. So the very physics that allows for its creation also mandates its immediate and violent execution. It is born and dies in the same quantum instant. It would never have time to draw in a neighbouring proton. It would never have time to establish a gravitational field of any consequence. It is a ghost in the machine, a momentary fluctuation of space-time that tears itself apart with its own incandescent fury. The predator, it turns out, is its own prey. The fear of a growing, consuming monster is replaced by the reality of a fleeting, self-annihilating spark. The theory that gave birth to the fear also provides the ultimate reassurance. And yet, a skeptic might still pause. They might say, this is only a theory. Hawking radiation has never been directly observed. What if Stephen Hawking was wrong? What if there is some unknown physical principle, some property of quantum gravity we don't yet understand, that makes these tiny black holes stable? It is a fair question. Science must always question its own assumptions. And to answer this, we don't look to theory. We look to the sky. We look for evidence written across the face of our own planet, our moon, and every other celestial body in our solar system. Because it turns out, the experiment we propose to run at the LHC is not a new one. Nature has been running a far more powerful version of it, continuously, for billions of years. And we are living, breathing proof of the results. We are under constant bombardment. Every second of every day, our planet is being peppered by silent, invisible bullets fired from the depths of space. They are called cosmic rays. These are not rays at all, but particles, mostly protons and atomic nuclei, that have been accelerated to tremendous speeds by the most violent and energetic events in the cosmos. Supernova explosions, the swirling accretion disks of black holes, the turbulent hearts of distant active galaxies. These are nature's own particle accelerators, and they operate on a scale that dwarfs our most ambitious terrestrial engineering. They are the messengers from cosmic cataclysms, and they travel across millions of light years to end their journey here, in a spectacular collision with the atoms at the top of our atmosphere. The energies involved are staggering. The Large Hadron Collider smashes protons together with a combined energy of around 13 tera electron volts. It is a phenomenal achievement of human ingenuity. But the universe is unimpressed. It has produced cosmic rays that have been detected striking our atmosphere with energies hundreds of thousands, even millions of times greater than what the LHC can achieve. A single one of these ultra-high energy cosmic rays can carry the kinetic energy of a well-pitched baseball, all concentrated into a single subatomic particle. When that proton from a distant galaxy slams into a nitrogen nucleus in our upper atmosphere, it is a collision of unimaginable violence. It is exactly the kind of event that, according to the theories we've explored, could potentially create a micro-black hole, and these are not rare events. Based on the flux of these particles, physicists have calculated that our atmosphere experiences hundreds of thousands of these LHC-equivalent collisions every single second. And the much higher energy collisions, the ones that make the LHC look like a child's toy, they happen less frequently, but they still happen. Over the Earth's 4.5 billion year history, it is estimated that the planet and its atmosphere have endured as many as a quadrillion of these collisions. That is a 1 followed by 30 zeros. An incomprehensible number of natural experiments, each one a potential roll of the dice. So, we must ask the obvious question. Where are all the black holes? If these collisions could create a stable, dangerous micro-black hole, The Earth should have been consumed billions of years ago. Our planet should be gone. The Moon, which has no thick atmosphere to protect it, is an even better cosmic ray detector. It has been directly impacted by these particles for eons, yet it remains, its cratered face, a silent testament to its own resilience. The continued existence of the Earth, the Moon, the Sun, and ancient dense stellar objects like neutron stars and white dwarfs, which are also constantly bombarded, serves as the most powerful, most compelling piece of observational evidence we could ever hope for. It is the result of the longest-running safety experiment in history, with a sample size larger than we could ever dream of producing. The cosmos has already run the experiment for us, over and over again, in conditions far more extreme than we can create on Earth. The verdict is in, written in the simple, undeniable fact of our own existence. The physicists at CERN are not reckless gamblers, playing dice with the fate of the world. They are careful detectives, following a trail of evidence that the universe itself has laid down for us. The safety of their work is not guaranteed by a line of code in a computer or a calculation on a whiteboard alone. It is underwritten by the silent, enduring stability of the cosmos itself. The two great pillars of reassurance stand firm: a theoretical shield forged in the mind of Hawking, which tells us that any micro-black hole would be a harmless, self-destructing flicker of quantum static, and an empirical shield built from 4.5 billion years of cosmic ray data, which shows us that nature has already performed this experiment and the world did not end. The fear then begins to recede. The chilling spectre of a doomsday machine dissolves into a far more subtle and beautiful picture of the universe's inner workings. The danger was a phantom, a shadow cast by our incomplete knowledge. But as the light of understanding grows brighter, the shadow shrinks, and in its place, a new question begins to form, one driven not by fear, but by an insatiable curiosity. If these fleeting microscopic entities are so utterly harmless, so ephemeral they barely skirt the edge of reality, then why on earth would we want to create one? What profound secrets could a ghost that lives and dies in a non-illionth of a second possibly have to tell us about the true nature of everything? The mathematics is a tapestry of breathtaking elegance. The theories, a set of keys to unlock deeper realities. But physics, in its heart, is not a spectator sport. It is an enterprise of action, of building and smashing, of asking the universe a question so pointed, so violent, that it has no choice but to show you its bones. To ask this question, we had to build an altar of incredible power, a circular cathedral buried 100 meters beneath the border of France and Switzerland, 27 kilometers around. This is the Large Hadron Collider at CERN, and for us, in our extraordinary quest, it is not just a machine. It is a cosmic forge, designed to replicate for the briefest imaginable instant the inferno of the Big Bang itself. Inside its chilled vacuum, colder than the void of deep space, we accelerate protons, the very hearts of atoms, to a velocity so close to the speed of light that their mass swells, their perception of time grinding almost to a halt. We guide them with thousands of superconducting magnets, powerful gravitational shepherds steering two beams in opposite directions, two swarms of microscopic bullets on a collision course. When these beams cross, in the heart of colossal detectors, a handful of protons from each stream will meet head-on. The impact is not a simple crash, but an act of annihilation. For a fleeting moment, the energy density at the point of impact is one of the highest we have ever created on this planet. In that instant, EAMC2 is not an equation in a textbook. It is a raw, elemental truth. Energy converts into a shower of new exotic particles, a momentary flower blooming from the soil of the quantum world. This is the brutal, beautiful art of particle physics, and hidden somewhere in the digital record of that fleeting blossom, we hunt for the ghost of a new kind of gravity. We are looking for the signature of a micro-black hole. This is not a search born of fear, but of profound hope. The creation of such an object would not be a catastrophe, but arguably the single greatest discovery in the history of science, a bridge between the two great pillars of modern physics. It would be the first tangible proof that gravity, the gentle force that holds you to your chair, can be unified with the chaotic world of quantum mechanics in the way our theories predict. So, what does one look for when hunting such an exotic beast? You cannot see a micro-black hole directly. It exists for less than a zeptosecond, a thousandth of a billionth of a second before it vanishes. Its existence is so ephemeral it can only be inferred from its death. And that death, according to the principles of Hawking radiation, should be spectacular. Imagine a typical proton-proton collision. It is a messy, directional affair. Energy and particles tend to fly out in focused streams, or jets, spraying forward along the original path of the protons. The resulting debris pattern is lopsided, chaotic, a testament to the glancing, complicated nature of the impact. But the decay of a micro-black hole should be utterly different. A black hole, as we've seen, has no memory of how it was formed. It is defined only by its mass, its charge, and its spin. Once formed, it is a perfect simple object. When it evaporates through Hawking radiation, it should do so democratically, radiating away its mass into all possible particles allowed by the laws of physics, with no preference for direction. The signature we search for, then, is a burst of exquisite symmetry. Instead of focused jets, we are looking for a spherical firework, an explosion of particles radiating outwards with high energy in every direction at once, a phenomenon physicists call isotropy. It would be an event of high multiplicity, meaning many particles, quarks, leptons, bosons, all born from a single, tiny point, a point that was, for an infinitesimal moment, a true singularity. It would be a whisper of the Big Bang itself, reenacted in the heart of a detector. In the torrent of data from hundreds of billions of collisions, such a perfectly spherical high particle count event would stand out like a supernova in a quiet suburban sky. It would be the first clue, the first scent of our quarry. But that is only one part of the forensic investigation. Our second signature relies on one of the most fundamental laws we know, the conservation of energy. What goes in must come out. The detectors at the LHC, like ATLAS and CMS, are masterpieces of engineering, designed as hermetic seals around the collision point. They're constructed in layers, like a vast metallic onion, each layer designed to catch and measure the energy and momentum of different types of particles as they fly outwards. We know with incredible precision the energy of the two protons going into the collision. By meticulously adding up the energy of every single particle that flies out and is registered by the detectors, the two sums should match perfectly. But what if they don't? What if, after our cosmic accounting is complete, we find that a significant amount of energy has simply vanished? This missing transverse energy is not a sign of faulty equipment. It is a profound clue, a phantom footprint in the digital snow. The theories of extra dimensions that make micro-black holes possible at these energies also offer a tantalizing explanation for where that energy might have gone. The graviton, the hypothetical carrier of the gravitational force, is special. Unlike all other known particles which are forever confined to our three-dimensional brain of space-time, the graviton is thought to be free to travel into the extra dimensions. If a micro-black hole forms and then evaporates, some of its energy could be radiated away in the form of gravitons. These gravitons would slip silently out of our detectors, out of our very dimension, carrying their energy with them into the higher dimensional space known as the bulk. We would see their absence. We would measure a gaping hole in the energy budget of the event. A perfectly spherical burst of many particles combined with a significant amount of missing energy would be a smoking gun. It would be powerful evidence that for a brief moment we had opened a gateway to another reality, and that something had slipped through. There is even a third, more subtle signature we can look for. It is a search not for a dramatic presence, but for a conspicuous absence. In the most violent proton collisions, we expect to see extremely high-energy jets of particles. These are the signature of direct, hard scattering between the quarks and gluons locked inside the protons. But if a micro-black hole were to form, it would act as an intermediary. The initial collision energy would be swallowed, captured by the event horizon before it could produce these powerful jets. The black hole would then thermalize this energy, essentially scrambling it, before decaying into a multitude of lower energy particles. So the third signature is a phenomenon called jet quenching. We would program our computers to search for events that should have produced high-energy jets based on their total energy, but for some reason did not. It would be like listening for a gunshot in a canyon and hearing only a diffuse echo, the sharp report having been mysteriously muffled, the silence where there should be a scream. This multi-pronged strategy, the search for spherical events, for missing energy, and for suppressed jets, forms the core of our hunt. It is a detective story being written at the speed of light, but the challenge is monumental, almost beyond human comprehension. The LHC generates up to 1 billion proton collisions every single second. Recording the data from every single one of these encounters is technologically impossible. The sheer volume of information would overwhelm all the storage capacity on Earth in a matter of hours. So, a complex multi-layered trigger system must make a split-second decision for each and every collision. In a fraction of a second, sophisticated algorithms analyze the raw data, looking for the telltale signs of interesting physics, high-energy deposits, unusual particle tracks, the very signatures we have just described. Out of 1 billion events, only about 1,000 are flagged as interesting enough to be saved for later analysis. It is an act of breathtaking computational triage. We are panning for grains of gold in a river the size of the Amazon, and we have to decide in an instant which handfuls of gravel are even worth a closer look. The fear that a truly revolutionary event might be missed by the trigger, discarded forever into the digital ether, is a constant nagging anxiety that haunts the sleep of every experimental physicist. From the petabytes of data that are saved, the real work begins. Thousands of physicists and graduate students from around the world dedicate their careers to sifting through these chosen events. They write code, build simulations, and calibrate detectors with a patience that borders on the religious. They are searching for a deviation from the known, a single anomalous chord in the symphony of the standard model. They are looking for our black hole. And so, after more than a decade of operations, after trillions upon trillions of collisions, after sifting through mountains of data with a fine-toothed comb, what have we found? The answer, so far, is a profound and eloquent silence. We have not seen it. Not a single, unambiguous, spherical, high multiplicity event. No undeniable evidence of energy leaking into other dimensions. The universe, at the energy scales we have probed so far, has not revealed this particular secret. And here, in this apparent lack of discovery, you might expect to find a story of disappointment, of failure. But that is not how science works. This null result is not an end. It is a crucial piece of the puzzle. It is, in itself, a discovery of immense importance. What this tells us is that the simplest, most optimistic models of large extra dimensions are incorrect. If there are extra dimensions, they must be smaller, more tightly curled up than we had initially hoped. The true energy scale at which gravity unifies with the other forces, the true Planck scale, must be higher than the reach of the LHC. We have not found the new continent, but we have charted a vast expanse of the ocean where it is not. We have raised the water level of our knowledge, forcing the shoreline of our ignorance to retreat. Each non-discovery constrains our theories, trimming the branches of possibility and forcing theorists back to their blackboards to devise more subtle, more sophisticated models. Perhaps the decay is not perfectly spherical due to the black hole's spin. Perhaps the cross-section, the probability of creating one, is far smaller than we calculated. The absence of evidence is not evidence of absence. It is a guide, a set of boundary conditions telling us where to look next and how. It has forced us to confront the possibility that the universe is more conventional than our grandest theories dreamed. Or perhaps it is even stranger, its secrets hidden in a way we have not yet developed the imagination to comprehend. This process of elimination, this slow, methodical mapping of reality, is the true engine of scientific progress. The hunt is far from over. The LHC is undergoing upgrades to achieve even higher energies and luminosities, creating more collisions and increasing the chances of witnessing a rare event. Physicists are refining their search algorithms, looking for more exotic and subtle signatures that might have been missed before. The data we have already collected will be analysed and reanalyzed for decades to come. a priceless archive of cosmic secrets waiting for a new idea, a new technique, to unlock them. The search for micro-black holes at the Large Hadron Collider has pushed our technology and our theoretical understanding to their absolute limits. It has forced us to ask some of the most fundamental questions we can pose about the nature of our reality, and the silence we have received in return is not empty. It is filled with information, with new constraints, with the hard-won wisdom of knowing where the dragons are not. It has reshaped our view of the subatomic world, reminding us that the universe is under no obligation to conform to our most cherished and beautiful theories. But in this grand intellectual struggle, in the very act of asking, we have deepened our understanding of the cosmos and our place within it. The quest has refined not just our physics, but our philosophy. For we are now faced with an even more profound set of questions that go beyond the search for a single particle or event. We are forced to wonder about the very structure of scientific knowledge itself. What does it mean when our most promising theories, the ones that resolve the deepest paradoxes, lead us to predictions that we cannot seem to verify? Where do we go from here? And so, after a decade and a half of listening intently to the subatomic thunder we created, the answer came not as a roar, but as a profound and telling silence. The data streams carrying the echoes of quadrillions of proton collisions contained no whisper of the transient microscopic voids we had sought, no signature of their spectacular decay, no hint of a gateway to another reality, no evidence at all for the birth and instantaneous death of a black hole here on Earth. The great hunt, which began in the farthest reaches of theoretical mathematics and sparked a very real and visceral fear across the globe, had reached its conclusion. And that conclusion, written in the cold, hard language of experimental data, was a resounding, unambiguous no. Yet to dismiss this result as a simple failure is to miss the point of the journey entirely. It is to misunderstand the very nature of exploration. We set out on this quest not with a guarantee of discovery, but with a question, a bold, audacious question that pushed our technology, our theories, and even our philosophies to their absolute limits. We asked if the fabric of our reality was more complex, more folded and rich with possibility than we had ever imagined. We asked if we could, for a single, fleeting moment, concentrate matter and energy so intensely that we might mimic the universe's most enigmatic creations. The answer we received was not the one many had hoped for, nor the one many had feared, but it was an answer nonetheless. And in science, a clear answer, even a negative one, is a precious gift. It is a new signpost on the map of reality, pointing us away from one path and inviting us to explore others with newfound wisdom. This journey, from a speculative glimmer in a theorist's equation to the very public crucible of the Large Hadron Collider, has been an epic in its own right. It's a story about how we confront the unknown, how we balance our insatiable curiosity with our profound responsibility. It forced us, as a species, to gaze into a theoretical abyss and ask ourselves if we were prepared for what might gaze back. The fear, we must remember, was not born of ignorance alone. It was rooted in a deep-seated, almost mythical respect for the forces we were attempting to unleash. The term black hole itself carries an immense gravitational weight in our culture, a signifier for the ultimate endpoint, for inescapable oblivion. The idea of creating one, no matter how small or short-lived, felt like a transgression, like stealing fire from a pantheon of cosmic gods we did not yet understand. News headlines, fueled by this primal apprehension, painted scenarios of a world devoured from within, a laboratory mishap escalating into a planetary catastrophe. The image was powerful, a man-made singularity, a seed of nothingness, falling to the Earth's core and consuming our world from the inside out. For a moment, the line between science fiction and sober reality seemed to blur, and the public alarm was a genuine expression of our anxieties about the ever-advancing frontier of human power. But science, at its best, is the ultimate antidote to fear. Not through dismissal, but through rigorous evidence-based understanding. The panic was met not with platitudes, but with the full, formidable weight of a century of physics. The first pillar of reassurance, and perhaps the most elegant, was a gift from Stephen Hawking himself. His revolutionary insight revealed that black holes are not the purely eternal prisons of classical theory. At the quantum level, they are not entirely black. They radiate. They glow with a faint, ghostly light, a thermal fizz of particles born from the roiling energy of empty space at their event horizons. And for a microscopic black hole, this glow would be no gentle shimmer. It would be a violent, explosive blaze. Hawking radiation dictates that the smaller the black hole, the hotter and more furiously it evaporates. A micro-black hole with the mass of just a few hundred protons would be a celestial blowtorch of unimaginable intensity, vanishing in a flash of gamma rays and other particles in less than a septillionth of a second. It would cease to exist almost at the very instant of its creation, long before it could ever interact with another atom, let alone pose any conceivable threat. It was a theoretical failsafe, a law of nature that ensured our creations could never become our devourers. The monster of our imagination was slain by the beautiful, subtle logic of quantum field theory. Even if, for some unforeseen reason, our understanding of Hawking radiation proved incomplete, nature had already provided us with a second, unassailable piece of evidence for our safety. We only needed to look up. For billions of years, the Earth has been adrift in a cosmic shooting gallery, constantly bombarded by particles from deep space called cosmic rays. These are the protons and atomic nuclei accelerated to incredible speeds by supernovae, by galactic magnetic fields, by phenomena so violent they make our colliders seem like children's toys. The highest energy cosmic rays strike our upper atmosphere with energies tens of millions of times greater than anything the Large Hadron Collider could ever hope to achieve. Each and every second, countless collisions of this magnitude are happening naturally above our heads. If high-energy particle collisions could create stable, dangerous micro-black holes, the universe would have already run the experiment time and time again. The Earth, the Moon, the Sun, and every star and planet in the cosmos would have been consumed eons ago. The continued existence of our planet, and of ancient celestial bodies like it, serves as the most robust safety certificate imaginable. We are still here. The Moon, with no protective atmosphere, has been absorbing these titanic impacts for 4.5 billion years, and its stoic, silent face remains. The universe itself had already performed the ultimate safety trial, and the verdict was in: the cosmos is safe from this particular doomsday scenario. Our experiments in the LHC are but a pale, controlled imitation of a natural process that has been a constant feature of our cosmic environment since time immemorial. We were not opening Pandora's box for the first time. We were merely peeking into a box that the universe had left wide open for billions of years. Finally, the third pillar of certainty was the data itself, the culmination of this entire endeavour. The search was not passive. It was an active, meticulous hunt through the debris of particle collisions. Physicists knew precisely what to look for. The explosive decay of a micro-black hole would be a spectacular, unmistakable event inside the colossal, cathedral-like detectors of Atlas and CMS. It would be a burst of high-energy particles, radiating outwards in a spherical, symmetrical pattern, an exotic firework unlike anything produced by the known laws of the Standard Model. They sifted through petabytes of data, developing sophisticated algorithms to search for this unique signature amidst the storm of familiar particle interactions. They looked for jets of matter, for high-energy photons, for leptons, for any sign of the new physics that a micro-black hole would represent. And they found nothing. Collision after collision, run after run, year after year, the result remained the same. The Standard Model, the familiar and well-tested theory of particles and forces, described everything they saw with unnerving precision. There were no spherical explosions, no hints of extra dimensions, no fleeting singularities. The silence from the detectors was the final empirical word, transforming a theoretical certainty of safety into an experimental fact. The fear had been confronted, analysed, and ultimately dispelled by the overwhelming power of reason and evidence. But what, then, is the legacy of this grand, expensive, and ultimately fruitless search? If we did not find what we were looking for, what did we gain? The answer is immense knowledge. Science often progresses as much by discovering where the truth isn't. as by finding where it is. The quest for micro-black holes, though it came up empty, was one of the most powerful diagnostic tools we have ever applied to the fabric of reality. The very fact that we did not find them has placed the most stringent constraints yet on theories involving large extra dimensions. It tells us that if extra dimensions do exist, they must be curled up far more tightly, on a scale far smaller and more energetically remote than many popular models had predicted. We have effectively closed a whole range of theoretical possibilities, forcing physicists back to their blackboards to devise new, more subtle and more clever ideas about the ultimate nature of space-time. This is not a failure. It is a crucial act of pruning the vast tree of scientific possibility, allowing new and more promising branches to grow. The search was a crucible that forged our technologies and techniques to an unprecedented level of refinement. In looking for the exotic signature of a decaying black hole, physicists had to understand the background noise of the standard model to an exquisite degree. This relentless drive for precision led to more accurate measurements of known particles and their interactions than ever before. The properties of the Higgs boson, the top quark, and the W and Z bosons were mapped with stunning clarity, reinforcing the foundations of our current understanding of the universe. The detectors themselves were pushed to their performance limits, their incredible sensitivity and speed honed by the search for this elusive signal. The computational grids built to analyze the torrent of data became wonders of modern information technology, pioneering techniques in big data analysis that have since found applications in fields far beyond fundamental physics. We went looking for a shortcut to quantum gravity, and while we did not find it, we returned with a map of the known world that was sharper, more detailed, and more reliable than ever before. It was like a 15th century explorer setting out to find a direct sea route to Cathay, only to fail, but in the process, producing the first truly accurate charts of the Atlantic Ocean. The destination was never reached, but the journey itself enriched the world immeasurably. The search for micro-black holes was a stress test of our most fundamental physical principles, and under that intense pressure, our theories held firm. We learned that whatever the solution to the grand mysteries of quantum gravity and the hierarchy problem may be, it is not as simple or as accessible as we might have once hoped. The universe, it seems, guards its deepest secrets more jealously. So where do we, the curious apes who dare to smash protons together, go from here? The null result from the LHC does not mark the end of our quest to understand the universe at its most extreme. It is merely the end of one chapter. The Great Ring near Geneva will continue its work, colliding particles at even higher energies and with greater intensity, seeking to uncover whatever secrets might lie just beyond our current reach. Future, even more powerful colliders are being designed, magnificent machines that will probe energies an order of magnitude higher, pushing the frontier of our knowledge even further into the unknown. They will continue to search for cracks in the standard model, for any hint of the new physics that we know must exist, the physics that will unite the quantum world with the gravity of Einstein. But our tools are also evolving. A new window onto the extreme universe has been thrown open with the advent of gravitational wave astronomy. We can now listen to the cosmic symphony of colliding black holes and neutron stars in distant galaxies. These cataclysmic events are nature's own high-energy experiments, and by studying the ripples they send through space-time, we may find clues to the nature of quantum gravity that are inaccessible to any Earth-based accelerator. The search for micro-black holes may have shifted from the collider halls to the quiet hum of laser interferometers, listening for the final moments of evaporating black holes from the very dawn of time. The dream of peering into other dimensions has not died. It has simply become more subtle, more challenging, and perhaps more profound. The fundamental questions that motivated the search remain as potent and as tantalizing as ever. Why is gravity so much weaker than the other forces of nature? What is the true nature of space-time at the smallest possible scales? Are there other universes, other realities, folded away just a fraction of a millimeter from our own? These are the questions that will continue to drive us, to inspire new theories, new experiments, and new generations of scientists. The search for micro-black holes taught us a valuable lesson in humility. It reminded us that the universe is not obligated to conform to our most elegant or appealing theories. The path to a deeper understanding is often winding and filled with dead ends, but each closed door, each null result is a vital piece of the puzzle. It is guidance from the cosmos itself telling us, no, not here, look elsewhere. Ultimately, this entire saga is a testament to the uniquely human spirit of inquiry. We are a species defined not by the answers we have, but by the questions we dare to ask. We look out at the vast, silent cosmos, and we do not simply accept it, we interrogate it. We build colossal machines to recreate the conditions of the first moments of time. We formulate theories of breathtaking mathematical beauty to describe realities we can never directly experience. We confront our deepest fears of the unknown not with superstition, but with reason, with experiment, and with a collaborative global effort of thousands of minds working in concert. The search for micro-black holes was a perfect encapsulation of this spirit. It represented our willingness to entertain a truly radical idea about the nature of our reality, and to then put that idea to the ultimate empirical test without flinching from the consequences. We did not find the phantom we were looking for. The veil between our universe and any potential others remains for now securely in place. But in the process of searching, we have illuminated our own world more brightly than ever before. We have demonstrated that our scientific reach is not limited by our fears, but is propelled by our courage to ask what if, and our determination to find out. The universe remains a place of profound mystery. Its deepest truths may be locked away in realms of energy and complexity that we have yet to even imagine. But we will continue to knock on the door. We will continue to listen at the keyhole, and we will continue to build ever more ingenious tools to pick the lock. For the quest for knowledge, the desire to understand our place in the cosmos, is the most powerful and enduring force we possess. It is our anchor in the vastness of space and time, and it is the light that will guide us, always, toward the next great frontier.